proper time to start. So it's a great pleasure for me to introduce our today's speaker, Professor John Perdew from Tulane University. He is one of the world's most cited physicists, and he is a professor of physics at Tulane University in New Orleans, where he given lectures. He has developed many of fundamental ideas and widely used approximations in density functional theory. He is actually one of pioneers of the density functional theory. He is author of more than 360 research articles, and which were cited already more than 400,000 of times. They were mostly cited by users of electronic structure codes that predict what atoms, molecules, solids, and liquids can exist and with what properties. By basing his approximations on exact conditions that he and others have derived, and upon approximate norms, he has facilitated efficient, predictive, and accurate descriptions of bonds without fitting to any modern system. And I think the topic of this talk is devoted exactly to this more predictive density functionals, symmetry breaking, and strong correlations issues. He has received honors, including membership in the National Academy of Sciences of United States in 2011, the Materials Theory Award of the Materials Research Society in 2012, the John Scott Award in 2015, the Mulliken Medal in 2018, and other distinctions. Recently, he has accepted our invitation to give a lecture talk at our seminar, and we're very happy that today we have him as a speaker at our seminar. So thank you again for accepting our invitation, Professor Perdew. The floor is yours.
Thank you, Andre. Trying to diminish, let's see this.
The slides look good, so in the
Yeah,
full screen
okay.
mode.
Okay, I think I can just move the picture off to the side a little bit. What I want to talk about today is more predictive density functionals, symmetry breaking, and strong correlation. I think these three subjects are closely related, and I'll try to explain that relationship in the talk that I'm going to give today. And I'd like to thank Andre for inviting me to give this talk. I also want to apologize to everyone who tuned in a week ago when I wasn't here, because I was simply very distracted. I had many deadlines to meet the day before, and I slept in and missed the talk. I'm very sorry for that. First time I ever did that in my life, and I hope to never do it again. Uh, okay. So I'll say a little bit about my university, Tulane University. It's located in New Orleans, Louisiana. We have opportunities. We have a PhD program. We have opportunities for graduate students and also for postdoctoral fellows. And we have about 20 faculty. Our theoretical faculty include Dennis Bondar in nonlinear optics, Ukrainian scientist who's now a faculty member in our department, Xiaokai Jian, who does many body physics. I do density functional theory. My wife, Adrian Roginski, does time-dependent density functional theory. And Jadwei's son, my former student and postdoc, is now also a faculty member, and he works on density functional theory, condensed matter, and materials theory. So let me begin by telling you a little bit about density functional theory. It's a theory that I guess the roots of the idea go back to the 1920s and the Thomas Fermi theory, but the formally exact theory was developed in the 1960s by Walter Cohn and Lou Sham and Pierre Hohenberg. And this exact Cohn-Sham density functional theory would predict the exact ground state energy and the exact ground state electron density for all materials, all molecules and all solids and all liquids and so on, within the Bohr-Oppenheimer approximation for the nuclear motion. So whether the material is a simple material or a complex one, this exact theory can predict the exact ground state energy and electron density through a self-consistent orbital theory that can be computationally efficient. The computational approach is simply to solve a one electron Schrodinger equations with an effective potential, to solve those equations self-consistently, as you would in Hartree-Fock theory. But unlike Hartree-Fock theory, this theory formally includes all the correlation effects. Once you get the orbitals, you can use them for many purposes, not just to construct the density and the kinetic energy of the electrons, but also to construct the you can use these orbitals to do full many-body theory, GW, and so on. So as a these exact early in the game, in the early 1970s, exact expressions were developed for the density functional for the exchange correlation energy. This is the many body part of the energy, and it's the only part of the energy functional that we don't know exactly in terms of the density and the orbitals. It has to be, we have exact expressions for it, but they're not practically evaluable without correlated wave functions. And the whole goal of density functional theory is to avoid the correlated wave functions. Because if you have many electrons, the wave function is a function of the coordinates of all the electrons. It becomes a very complicated object to compute and store. The density is simpler because it's just a function of say 3 coordinates, position coordinates x, y, and z, for instance. So we know the exact exchange correlation energy in terms of a constrained search over correlated wave functions, but that's not practical. What we need to do to make this theory practical is to approximate that the density functional for the exchange correlation energy. The existence theorems from the 1960s motivate us because we know that there is an exact expression, and that motivates us to make better and better approximations. And it also motivated the derivation of many of the exact mathematical properties of this functional. About 20 of them are known, and the approximations can be constrained to satisfy those exact conditions, which makes them more predictive, as I'll try to establish. So sometimes I'll talk about simple materials and complex materials, and the distinction I'm making there is that the complex materials typically are sensitive to small energy differences, and the functional has to be very accurate to describe those small energy differences well. For instance, if you have competing states or phases for the states that compete to be the ground state or that compete to be the equilibrium state at a finite temperature, then you need a very good functional to describe those effects. Another approach to many complex materials in condensed matter physics is to make a model Hamiltonian with fitted parameters. You can learn and understand from that, but those approaches are not very useful for predicting new materials. I think density functional theory is useful for predicting completely new materials. So how do we construct the approximation to the density functional for the exchange correlation energy? That's the only approximation we really have to make. And there are two standard approaches. The first one, which is more of a chemistry-based approach, is to fit a data set of real bonded systems. Typically, there's a lot of accurate information for the energies and energy differences of molecules in chemistry. You can design a functional form with parameters and adjust them to fit that data. And often this approach satisfies a few exact constraints and appropriate norms as well. It would be much harder to do this without them. I would say that this approach is an interpolative approach because it's the more accurate approach for systems that are similar to the ones you have fitted. And machine learning is a new and powerful way to do this. Second way, a second approach is to satisfy as many exact constraints as possible. The exact constraints are the known mathematical properties of the exact density functional. There are about 20 of them. They include equalities, bounds, scaling relations, limits, and so on. Many of them were derived by my former Tulane colleague, Mel Levy. So, I've derived some of them. Elliot Lieb has derived some, and others as well. And in addition to the exact constraints, at the higher levels of functional approximation, it's very helpful to have appropriate norms. Appropriate norms are non-bonded systems for which the approximation should be very accurate. I emphasize non-bonded because we want to predict bonds, so we don't want to input information about bonds to the functional if we can avoid it. The first appropriate norm was the uniform electron gas, whose energy is known very accurately. But there are others that I'll tell you about later. So this second approach is, I would say, a more first principles approach, which is more widely predictive because the exact constraints are universal and they apply to everything. It predicts and doesn't fit bonds. So how accurately can we predict over the immense space of possible bonded materials? I'll try to answer that question too at some level in this talk. So let me summarize some of the computationally efficient semi-local density functional approximations that are constructed by this constraint-based approach. Semi-local here means that the exchange correlation energy is approximated as a single integral over the three-dimensional space of a function that can be obtained from information either at each point in space or in an infinitesimal neighborhood of that space. So that includes the density, its derivatives, the orbitals, the derivatives, the orbitals, and so on. The first useful density functional for the exchange correlation energy was the local spin density approximation from Cohn and Sham. They proposed it in 1965. The inputs to that approximation are the exchange and correlation energies per particle of a uniform electron gas. Those numbers were improved up to about 1992, and they're now known very accurately. So there was a single appropriate norm. We simply make the functional exact for the uniform gas and see what we get. That turned out to be surprisingly accurate, and later it was understood that that's because this functional inherits the satisfaction of 9 of the known exact constraints from the uniform gas appropriate norms. A second functional that I'll mention here is the Perdew-Burke-Ernzerhof, or PBE, generalized gradient approximation from 1996. That adds to the exchange correlation energy density a second ingredient. The first ingredient are the local spin densities n up of R and n down of R. They're present even in the LSDA. The next natural thing to add were the gradients of the local spin densities at the point R, and that's what this PBE functional did. It was constructed to satisfy 11 exact constraints and the uniform gas appropriate norm. There were no other appropriate norms in PBE, just the uniform gas. But some of the exact constraints were enforced explicitly. There's SCAN, the strongly constrained and appropriately normed meta-GGA. That comes from Janway's son, Adrian Rzyński, and myself in 2015. It was designed to satisfy all of the 17 exact constraints that a meta-GGA can satisfy. There are about 3 exact constraints that require a fully non-local functional, and the meta-GGA can't satisfy those. The appropriate norms were expanded in SCAN to include not only the uniform electron densities, but also closed subshell atoms like the rare gas atoms. So what all these functionals have in common is that they are not fitted to any bonded multi-center system. There's fitting the uniform gas. There's also fitting to rare gas atoms. Now, the errors decrease in this sequence as we satisfy more exact constraints, more appropriate norms. The errors of the functionals decrease. And in particular, the self-interaction error, which I'll talk about later, decreases in the sequence from LSDA to PBE to SCAN, and then to the hybrid functionals that include some exact exchange. Typically, hybrid functionals cannot be constructed without some fitting to bonded systems. So let me review this a little bit about the SCAN construction. There are some exact constraints that apply to all electron densities, and then there are some exact constraints that cluster around either the slowly varying densities, the densities that vary slowly over space, and are therefore, in some sense, close to the uniform electron gas, or the 1 and 2 electron densities. So we can construct simple functionals for each of these 2 cases, and then we can interpolate between them and extrapolate using a dimensionless function of position alpha, which is constructed from the local spin densities, the gradients of the local spin densities, and also the positive orbital kinetic energy densities. In cone-sham density functional theory, we have the occupied orbitals. We've solved for them. We can use them to construct a non-interacting kinetic energy and a non-interacting kinetic energy density. And with those 3 ingredients, we can combine them to make a dimensionless variable that can recognize 1 and 2 electron densities by the condition that this parameter alpha is 0. They can recognize slowly varying densities by the condition that this parameter alpha is close to 1. They can also recognize density tail overlap regions by the condition that the parameter alpha is somewhat bigger than 1. Alpha intrinsically varies from 0 to infinity. It's an intrinsically positive or non-negative quantity. So SCAN interpolates between the first 2 regions, and it extrapolates to the 3rd region, the density tail overlap region. SCAN is not exact for all 1 electron densities because that requires a fully non-local functional, but it is accurate for all 1 electron densities that are compact, like the density of the hydrogen atom or the density of the helium atom or a 1 electron Gaussian density. It's accurate for all those things. Okay, I will take questions at the end, but if you'd like to ask brief questions during my talk, I can also try to answer those. I also wanted to check to make sure that you're still hearing me and seeing the slides. Is it okay?
Yeah.
It's okay?
Question.
Yeah. Everything
Okay.
works well. And yeah, question, please.
Sure.
Well, my question is, you are talking about orbital kinetic energy. Is it around some atomic center or in a more generalized sense?
It's in a more generalized sense. So
Okay.
if you know the orbital, if you know the cone-sham orbitals, you can find the cone-sham orbitals for
Okay.
any system. It can be an atom, a molecule, a solid. And when you take the gradient of each occupied orbital and square it and multiply by 1/2 and sum over all the occupied orbitals, that gives you the kinetic energy density.
Yeah, thank you.
Non-interacting kinetic energy density. There's also an interacting part of the kinetic energy density, which gets subsumed into this exchange correlation energy that we approximate.
Maybe one more question about exact
Sure.
constraints. You mentioned that there are 17. Is there a upper bound somehow fixed, or it just by construction?
There's a lower bound on the exchange correlation energy. It's a good question. There are several lower bounds on the exchange correlation energy, and they're very valuable because the exchange correlation energy of any system is bounded from above by a constant times the LDA exchange energy, the local density approximation for the exchange energy. So this bound is a very natural one for density functional theory. And we have a loose version of that bound that was derived by Lieb and Oxford, and then there's a tighter version of this bound just for the exchange energy. So the exact exchange energy is rather closely bounded by a constant of order 1 times the local density approximation for the exchange energy. Those bounds are all built into the functional.
Okay.
Okay.
Thank you. Yeah.
All right. Thank you. So let's go on. I'm going to review some of the successes and failures of SCAN. First of all, it's much better than previous semi-local functionals, including PBE, for a lot of properties that I'll list here. Liquid water and liquid water at interfaces, at solid interfaces, they're much better described by SCAN than by PBE. Ferroelectric materials, where the spontaneous dipole moments appear inside the material, it's a kind of symmetry breaking, described much better by SCAN than by PBE. The formation energies and the ground state crystal structures of strongly bonded solids are much better than in PBE, which is important because if you want to be able to predict what solids are stable, which is important for any application, then you need to be able to make a correct prediction of these quantities, including the crystal structure. There are critical pressures for structural phase transitions of semiconductors that are much better. There are some strongly correlated materials, including some of the phases of manganese dioxide and many of the cuprate high temperature superconducting materials, which are much better described by SCAN than by PBE. And in particular, in the cuprate high temperature superconducting materials, we find that the pristine or undoped material is correctly an insulator with SCAN, and that when you dope with strontium or something like that, the gap gradually closes and the material becomes a metal, and in the metallic state, the superconductivity can appear. Get the correct spin moment on the copper atom, we get stripes and stripe fluctuations of patterns of spin magnetization. There are the geometric and mechanical properties of many materials, including the two-dimensional materials, surface energies of metals. All these things are much better in SCAN than in PBE. We believe as a consequence of the satisfaction of more appropriate norms and more exact constraints. Here's a slide about the high temperature cuprate material, lanthanum copper oxide. And you can see the crystal structure in the middle here. Each copper atom is surrounded by 6 oxygen atoms. There are also some green lanthanum atoms in the pristine material, and in the doped material, you replace some of those lanthanum atoms by strontium atoms, maybe 25% of them. And on the left side, you see the density of states for this material calculated at 3 levels of density functional approximation. This material is really an insulator with a gap of about 1 electron volt or more. The local spin density approximation and the Perdew-Burke-Ernzler-Hoff generalized gradient approximation both make it a metal. You can see that at the Fermi level, which is the energy zero here, there's a non-zero density of states from both those functionals. When we use the scan functional to do this calculation, this is actually, I'm not an author of this paper, but James Furness was the first author. Excuse me. You can see that a gap opens up, and it's a large gap, about 1 eV, roughly like the experimental one. Now, when you start doping with strontium, this gap gradually closes, and at 25% strontium, which is the experimental critical concentration, this material becomes a metal, and then it can superconduct. In chemistry, SCAN is also very good. It was tested on Stefan Grimma's large GMTKN 55 suite of 55 molecular data sets, measuring different properties of molecules. SCAN turned out to be the best meta-GGA tested. It was competing against many others, including some of our earlier non-empirical ones, and also some empirical ones that were heavily fitted, and it outperformed all of those meta-GGAs. It was, however, outperformed by a few of the hybrid functionals. But when there's a special set of the GMTKN 55 called the mindless benchmarking set. And in spite of the funny name, it's not mindless. It's a set of artificial molecules, which are not normally seen in nature because they're less stable than other molecules that can form. But they are either stable or metastable. And they can be calculated by highly accurate correlated wave function methods. Their properties can be calculated, and you can use them to test functionals. And these molecules have never been used to fit any functional, because they're artificial. So in that set, SCAN actually outperformed all the other functionals, including all the hybrid functionals. And I think this shows, in a way, the predictive power of the exact constraints. You can apply a functional based on the exact constraints, can make predictions for materials that are quite different from anything that it has been designed to work for. Say a little about the hybrid functionals. They're typically fitted to multi-center bonded systems like molecules. They're often computationally expensive because they're fully non-local. They're accurate for many molecules, not for these artificial ones, but for many real molecules. But often they're not so good for bulk materials, particularly metals. Hybrid functionals have a lot of trouble with describing metals correctly. Okay, so now, for some reason, I can't move forward anymore. There. Okay, so I got out of that, and now I've got something on the screen. Do you see that? Try to move it up here and off if I can.
No, the slide seems clear.
Okay, for me, something is blocked, but I can't see how to. It's like a little version of the same screen, which is on top of the big screen.
The pointer doesn't move.
The pointer doesn't move. No, so I can move it up, but I can't move it out. So I'll just do the best I can. So this is the rest of the story about scan. It isn't better than PBE for everything. Whoops. So I moved it down to the bottom, strangely enough. Okay, so scan is somewhat better than previous semi-local functionals, just slightly for the band gaps of solids. The original Kohn-Sham theory, the exact Kohn-Sham theory, doesn't give band gaps of solids correctly because the effective potential is local, and you need a non-local potential to get correct band gaps. If you but scan is not exactly implemented in the original Kohn-Sham scheme. It's implemented in what's called the generalized Kohn-Sham scheme, in which you would allow the effective potential that the electrons see to be a non-local operator, like a differential operator or an integral operator. And in the generalized Kohn-Sham scheme, you can get accurate band gaps. And what happens is when you evaluate scan and self-consistently in this generalized Kohn-Sham scheme, is that the band gap opens up, it moves in the right direction to create agreement with experiment, but it doesn't go far enough by any means. But it's still an improvement. And for many transition metal oxides, these are insulating solids. These are materials where semi-local functionals often are corrected with a Hubbard U or a plus U correction, which we can think of as a kind of self-interaction correction. In these transition metal oxides, scan often needs a plus U correction. Sometimes it doesn't. Often it needs one, but the one it needs is smaller than the one needed for PBE. So there's some improvement in the description of these strongly correlated transition metal oxide systems. It's somewhat worse than PBE or Laplacian level meta-GGAs for some systems and properties. For instance, for transition some transition metal properties like the properties of iron, you can make errors in formation energies, magnetic properties, vacancy formation energies that are bigger than the errors of PBE. They're not huge errors, but it's disturbing that happens. I think I know why that is. Also, scan makes some extra demands on the mesh for the integration over the real space to find the exchange correlation energy. And it also makes some problems for pseudopotential construction because the original scan functional was designed to have some relatively non-smooth features in order to satisfy all the exact constraints. So we have fixed those numerical problems with scan by creating a smooth R2 scan in 2020. And that functional has essentially the same accuracy as scan, or perhaps slightly greater accuracy, but it also has greater smoothness, which makes it computationally more efficient and more useful for pseudopotential construction. So if I summarized all this, I would say that the 2015 scan functional and the 2022 R2 scan reformed scan functional. These are both meta-GGAs. what makes them meta-GGAs is that they use the orbital kinetic energy density as an ingredient of the exchange correlation energy. They're usually more accurate than the Perdew-Burke-Ehrnzer-Hoff GGA for a modest, maybe factor of 3 increase in computational cost. And without being fitted to any multi-center bonded system, they describe diverse bonds, including covalent bonds, metallic bonds, hydrogen bonds, intermediate range van der Waals bonds. Of course, we don't capture the long range van der Waals interaction, which requires a fully non-local functional, but you could add that in as an additive correction to scan or R2 scan. This scan functional has been adopted by the Materials Project at Berkeley. They have a website where they list the computed properties of about 146,000 known solids. These are all solids that have been observed in nature, and they've compiled their computed properties. Originally, they used PBE and PBE plus U. Now they're using scan without the U correction, and it seems to be better. There was also a recent Nature paper in 2023 in which scan was used to validate the neural network predictions for 2.2 million stable solids. Now, you can't do electronic structure calculations for that many solids, but you can do machine learning calculations, and you can check them for some solids using the scan functional, and that's what they did. Okay, so I will continue here. Maybe this is a good place to see if there are other short questions. Long questions I'll take at the end. Are there any short questions?
Short question. What does the word scan mean?
I didn't explain that. Yes, okay. So SCAN is an acronym. And we used to name the functionals for the authors, but with SCAN, we decided to try to change that practice and use something more descriptive. So SCAN stands for strong. The SC is for strongly constrained, and the AN is for appropriately normed. So it's the strongly constrained and appropriately normed meta-GGA.
If I may, yeah. I'm not sure whether it's a long or short question. So the question is short, but the answer may be long.
The answer could be long. I understand.
Yeah. So I mean, you say that scan still underestimates Coulomb interaction for transition metal oxides. Is there a way to go further to proper U?
Yes, that's a very good question, and I'll try to say something about that at the end of my talk. But I think the way to do that is to make what I would call a proper self-interaction correction. So a self-interaction correction to any functional would make that functional exact for all one electron densities, no matter what their shapes. If they're one electron densities, the functional would be exact for them. That's an exact constraint, but it's one that can only be satisfied at the level of a non-local functional. And we know how to make those self-interaction corrections. We've known that for 40 years. But the problem has been that when we make the functional exact for one electron densities, we make it wrong for the slowly varying densities where it works well. And so we often degrade the performance of the functional by doing that. I think the way to fix this problem for the transition metal oxides is to make a self-interaction correction that does not lose the correct slowly varying limit. And I'll say more about that later. Okay. So the next part of my talk is about symmetry breaking and how it's related to strong correlation in density functional theory. So let's start with quantum mechanics. Quantum mechanics suggests that if we have any isolated finite system, it has a symmetry unbroken ground state wave function. Now that wave function may be either normally correlated or strongly correlated. It can be strongly correlated if the corresponding cone-sham non-interacting system. So in density functional theory, we make a non-interacting system that has the same electron density as the interacting system. And we use that density and also the orbitals for that system to construct the energy of the interacting system. From a wave function point of view, you could imagine starting with the uncorrelated system, and then turning on the electron-electron interaction continuously to get to the interacting system. And if you do that, if the non-interacting system is non-degenerate, then you expect to get normal correlation that turns on gradually and isn't terribly strong. But if the non-interacting system is degenerate with other non-interacting systems that can be mixed with it through the Coulomb interaction, then you can have strong correlation. And strong correlation has always been a challenge to density functional theory. Sometimes people define it as everything that density functional theory gets wrong, but I don't define it that way. Because in principle, density functional theory should get everything right, at least at the ground state level. So if you have a nearly degenerate ground states of the non-interacting system and they're mixed strongly by the Coulomb interaction, you can get this strong correlation. Now, standard approximate density functionals capture normal correlation, but they don't capture strong correlation. That's because the appropriate norms are all normally correlated. The uniform electron gas, the rare gas atoms, they're all normally correlated. But a good density functional can often capture the ground state energy of a symmetry unbroken, strongly correlated state. This has been found by experience. It does that by yielding a symmetry broken, normally correlated state. In other words, typically what happens is that some symmetry, like the symmetry of the spin density, breaks, so that a singlet state, which would normally have zero net spin density, suddenly has non-zero net spin density, like as in antiferromagnetism, for instance. And this symmetry breaking can break the degeneracy that caused the strong correlation and take you back to a normally correlated system. And that if that normally correlated system has an energy close to the strongly correlated system, then your density functional has described the energy of a strongly correlated system by breaking the symmetry. I'm not sure how reliably that happens, but it happens in many cases. It happens with remarkable accuracy. I'll talk about some of those. So symmetry broken ground states are not true eigenstates in finite systems. They're states that have small energy uncertainties, and therefore they have lifetimes by the energy time uncertainty principle. And those long lifetimes can increase with the system size. So Phil Anderson, back in 1972, argued that symmetries break in real systems. They break observably when the time-dependent density or spin density fluctuations that are present even in the ground state and are accessible by time-dependent density functional theory drop to low frequency or zero frequency. And he argued that antiferromagnetism in a solid is a symmetry breaking that is certainly real and observable and can persist at least for years. So I want to talk about an example of symmetry breaking where we can actually investigate how that happens. This is a static charge density wave that breaks the translational symmetry of a low density uniform electron gas, or gellium. So we start with a gellium which has a uniform positive background, which is just imitating the external potential. And we have electrons that neutralize that background. And at normal densities, the electron density will also be uniform. But if you take the background to very low densities, then it's known that the electron density will crumple up into a charge density wave. That was found in the quantum Monte Carlo calculations by Seproli and Alder in 1980. and they predicted a transition at a density parameter Rs. Rs is roughly, very roughly, the average distance between electrons. When that distance is something between 65 Bohrs and 100 Bohrs, this transition is found. It's found with the wave vector, which is about a little more than 2 times the Fermi wave vector of the uniform gas. And so we can study this translation by using the density response function. The density response function can be defined for static external perturbations in ground state DFT, and it can be defined for time-dependent external perturbations, perturbing potentials in time-dependent DFT. And we usually use Fourier transform variables. So we transform the spatial coordinates to a wave vector, and we transform the time to a frequency. And then in a uniform, if we're looking at the density response of a uniform gas, for instance, we can write that an infinitesimal external perturbation V with wave vector Q and frequency omega creates a time-dependent infinitesimal density response, delta n, with the same wave vector and frequency. And the proportionality constant is this density response function chi, which depends on the density of the uniform gas, the wave vector of the perturbation, and the frequency. And we can find this response function from a Dyson equation, which says that if you know the Kohn-Sham or non-interacting response function chi 0, if you know the Coulomb interaction, whose Fourier transform is 4 pi over q squared, and if you additionally know an exchange correlation kernel fxc of q and omega, which is the effective exchange correlation interaction between electrons in some sense, then we can find chi from chi 0 through this Dyson equation on the bottom of the screen. Now, we have done that because we can do that for the uniform gas. So we modeled this exchange correlation kernel to satisfy exact constraints. So this was done with Adrian Roginski and other co-authors in 2020. We used the same constraint satisfaction approach. We took all the known constraints on the uniform gas kernel that have been derived over the years, and we made a model that satisfies those constraints. And then we constructed the static or zero frequency response function and also the time-dependent or frequency-dependent response function. We can look at this symmetry breaking from 2 different points of view. The first is the ground state density functional point of view, where the external perturbation is static. If that external perturbation is 0, but it still produces a non-zero infinitesimal or finite charge density change, then that's a symmetry break, a spontaneous symmetry breaking that can occur even in the absence of a symmetry breaking external potential. And the way that has to happen, if it happens, is through the divergence of this density response function chi. So with our time-dependent chi, we found that this time-independent chi diverges when the uniform gas is at a density of Rs equals 69 Bohr. That's the average distance between electrons. And when the wave vector of this density wave is a little more than 2 times the Fermi wave vector, just almost exactly like what they found in quantum Monte Carlo, which is a wave function calculation. You can also do time-dependent density functional theory to check Anderson's interpretation, because in time-dependent density functional theory, there's a spectral function S of Q and omega, which is proportional to the imaginary part of chi. And what we found is that this spectral function becomes concentrated at 0 frequency when the wave vector Q is 2.3 times kF and when Rs is 69. And that confirms that Anderson was right. There's a there are time-dependent density fluctuations in the ground state of the uniform gas, and one of a fluctuation of a particular wave vector drops to zero frequency at the transition to the charge density wave. So loosely speaking, we can say that the charge density wave is a soft plasmon. It isn't really a plasmon; it's a soft density fluctuation, but soft plasmon-like density fluctuation. And that work was published in 2021 in the Proceedings of the National Academy of Sciences. So here's a figure that shows what happens there. The horizontal axis is wave vector q divided by Fermi wave vector kf. And the vertical axis is a dimensionless average frequency for a density fluctuation of wave vector q. Now, if you go to small wave vectors q close to zero, these are actually excitations of the electron gas. They're plasmon excitations of the electron gas, and so each plasmon of wave vector q has a single well-defined frequency, which at small q is the plasmon frequency. So we see this ratio of the average frequency of a fluctuation to the plasmon frequency going to zero when q goes to zero, going to 1 when q goes to zero. If we increase q, we can see that the plasmon disperses upward at a normal density like Rs equals 4 Bohr, which is the density of sodium metal, for instance. It has an upward plasmon dispersion, just as our model predicts. If we go to a very low density like Rs equals 69, where we predict that this charge density wave appears, you can see that the plasmon dispersion is downward. The solid yellow line is the plasmon dispersion. At some point, that plasmon enters a particle hole continuum, and then we're not looking at excitations, we're looking at time-dependent fluctuations. But the average frequency of such a fluctuation continues to drop, and it drops to zero around q over kf equals 2.3. So Anderson was really exactly right in his interpretation, at least for this kind of symmetry breaking.
Pardon. Is this commensurable with the sort of lattice constant, this zero location, or not?
Is it consistent with the lattice constant? Okay, in gellium, this is gellium or uniform electron gas, so we don't actually have a lattice. What we have is a positive background. So it's like taking the densities of the positive ions and smearing them out into a uniform positive background, where we don't have a lattice anymore. We have actually translational symmetry of the external of the Cohen-Sham effective potential.
Could there be a kind of Wigner crystal?
Yes, there can be. Yes, that's right. Okay. Now I understand your question. Yes. This charge density wave is the beginning of the Wigner crystal, because there's not just one wave vector, but there are many wave vectors that have the same. This happens at many wave vectors. And when you superpose those wave vectors, you make a lattice. You make an electron lattice, and that's the beginning of the charge density wave, which is also a symmetry breaking. That's the beginning of the Wigner lattice, which is also a symmetry breaking. Okay, so I'm running late. I think since probably I'll skip over some things here. I'll just briefly mention that there are some strongly correlated. There's some molecule. Most systems that are strongly correlated have d or f electrons, but the phenomenon of strong correlation can also happen in systems that only have s or p electrons. And the ground state of the carbon dimer, which is a singlet ground state, is an example of a strongly correlated molecule, sp bonded molecule. Wave function calculations show that. We can see that with SCAN, because SCAN is usually very accurate for atomization energies with a mean absolute error of something like 1/10 of an electron volt, much less than Hartree-Fock, LSDA, or PBE. But C2 is a kind of exception if we don't let the symmetry break. If we constrain the spin density of the net, if we constrain the local spin density to be 0 to describe a singlet state, the singlet symmetry, then there's a huge error in the SCAN binding energy, and SCAN is underbound by about 1.4 electron volts, which stands out dramatically in comparison to the 0.1. If we let the symmetry break, we actually get the right atomization energy for C2, which is 6.2 electron volts from the full CI quantum Monte Carlo calculation. It's also 6.2 with SCAN if we allow the symmetry to break. This is also a case where you get better and better descriptions of the symmetry, the energy of the symmetry of the strongly correlated state if you let the functional improve from LSDA to PBE to SCAN. And I think the last thing I want to talk about today will be the full non-locality. So the functionals that we have so far are all semi-local in the sense that they're all single integrals over three-dimensional space of some function that depends on a quantity that is well defined at each point R and that can be found from an infinitesimal neighborhood around R. But there are some exact constraints, such as exactness for all one electron densities and correct behavior for non-integer particle number in open systems, where you need full non-locality. So I call that the old and new frontier. It's old because we've known this for more than 40 years, but it's still new because we haven't solved the problem yet completely. So back in 1981, I had a paper with Alex Unger about self-interaction correction of the local spin density approximation, which was the only functional known at that time. And what this self-interaction correction does is it takes any approximate functional of the form that you see here, and it makes it exact for the ground states and even for the excited states of any collection of non-overlapped one electron densities. And it gives no correction to the exact functional. It's designed to do that. It typically improves the local spin density approximation for atoms and molecules. It led to the discovery that the exact energy of a many electron open system varies linearly with the average electron number between adjacent integers. This was one of those rare cases where an approximation led to led after some work to an exact result. The piecewise linearity of the energy as of the exact total energy as a function of electron number. It's piecewise linear between integers and has derivative discontinuities at the integers. So the form of this Perdew-Unger self-interaction correction is shown in the top line here. You start with the approximate functional and you add a correction to it. The correction is a sum over contributions from occupied orbitals. For each occupied orbital, we find an electron orbital density, Ni sigma, and we subtract off the Hartree energy of that orbital density, and we subtract off the approximate exchange correlation energy of that one electron density. And that makes the functional exact for all one electron systems, because in a one electron system, the exchange correlation energy simply cancels the Hartree energy, Hartree electrostatic energy. And the electron then just sees the external potential and itself. So, excuse me. So one complication there is that you have to have localized orbitals, and the cone-sham orbital densities can be delocalized. So what we typically do is make a unitary transformation of the occupied cone-sham orbitals, which I'll call psi alpha sigma of r, to minimize the self-interaction corrected total energy. And the simple unitary transformation was proposed by Mark Peterson, Adrian Rzyński, and I in 2014. That's the one we are using currently. Now, the paradox of self-interaction correction is that the PZSIC improves any approximate functional in situations where its self-interaction error is a dominant error. For example, for stretched radical bonds, stretched bonds with spin density, for transition states of chemical reactions, for charge transfers, and so on. For these problems, the predominant error is the self-interaction error, and it's improved. That error is reduced by this Perdew-Unger approach. But then there are many other properties which have a very small self-interaction error, like the equilibrium geometries and the energy differences for simple molecules or solids. There, the Perdew-Unger self-interaction correction often worsens the PBE GGA and even the scan meta GGA. It seems like the better the functional is for equilibrium properties before we make this self-interaction correction, the more those properties get worsened or degraded by the Perdew-Unger self-interaction correction. And the root of that problem is that the Perdew-Unger self-interaction correction loses exactness for the uniform electron gas. That was shown by Biswajit, Santra, and I in 2019. It's exact if applied to the uniform electron, to the exact functional for the uniform gas, but if you apply it to a good approximate functionals for the uniform gas, it makes big errors. And this problem can be eliminated without losing the correct features of the Perdew-Unger self-interaction correction if you locally scale down the Perdew-Unger self-interaction correction towards zero in many electron regions while keeping a full correction in one electron regions. This approach leads to good results so far only for the correction of the local spin density approximation in equilibrium bonds. And so we're working now on trying to make the self-interaction correction work with the scan and R2 scan functionals. And I think we made some progress on that, but the work is not done yet. I'm going to skip over this one and come to my summary because I've used up too much time here. Summary. Density functionals for the exchange correlation energy of a many electron system become more accurate, more widely predictive when they're designed to satisfy more exact constraints and appropriate norms. I'm convinced that that's true because I've seen that happen over and over again over time, over a long lifetime. Scan is a good but imperfect, non-empirical, semi-local, and hence computationally efficient functional. Much of the full non-locality of the exact functional can be restored by making a modified Perdew-Unger self-interaction correction to R2 scan that doesn't lose the correct slowly varying limit. And we're working on that. We don't have it yet, but I think we can have it. And finally, density functional theory with symmetry breaking is starting to correctly describe the ground states of both simple and complex systems, including the strongly correlated systems. I don't know how far we can go with a good functional plus symmetry breaking. I'm trying to find out, but I'm hopeful that that approach will work for everything. So I'd like to thank you very much for your patience and your time. And if you have questions, more questions. The earlier questions were good, but if you have more questions, I can try to answer them. Thank you.
Thank you very much for a wonderful talk. We have already two raised hands. I think Mykola Bondarenko was the first with the raised hand.
Thank you. Thank you very much. I was very interested, though I'm not an expert in this field. Concerning the self-interaction problem, I'm also puzzled. It seems to me, for example, if we put it to an extreme, if we apply the density functional theory to a single hydrogen atom, then we have some excessive self-interaction. The electron density acts on itself, so electron self-repels, whereas in reality, we only have to only electron nucleus interaction has to remain.
Right.
So it seems to me that because of this, DFT is in a serious trouble when applied to substances containing hydrogen, essentially. For instance, you mentioned this water, and is that so? Because I often see papers in physical review where hydrogen is essential in the problem, or there are fast protons passing through the substance in time-dependent DFT or helium atoms like that.
Right. Mm-hmm. Yeah. So that's right. Everything you said there is true. The more advanced functionals like R2 scan give a very accurate description of the hydrogen atom. The energy of the hydrogen atom is almost exact in R2 scan. The hydrogen molecule H2 is almost exact in R2 scan, and the reason is that those two densities for the hydrogen atom and the hydrogen molecule are compact densities, compact 1 electron density, compact 2 electron densities. And for such compact densities, R2 scan is designed to be very good. Where the failures appear in other cases, for example, if you take H2 plus, which has 1 electron and 2 protons, and if you stretch out the distance between the 2 protons and create a stretched bond, then scan functional will start to fail. Its errors will get bigger. Its errors will be small at the equilibrium bond length of H2 plus. But as you stretch out the bond length, the errors will grow and grow. The energy will get too low compared to the approximate energy will get too low compared to the exact one. And the reason is that the 1 electron density in that case for stretched H2 plus is not compact. It's lobed. It's concentrated in one lobe around one proton and one lobe around the other proton. That's the situation for which the self-interaction correction is needed now, even for R2 scan. It's for 1 electron, we don't need it for all 1 electron densities, but we need a self-interaction correction for 1 electron densities that are non-compact, that have lobes or stretch bonds, features like that.
Oh, thank you. I have another related question.
Sure.
It's about the situation when the processes are quick. We are not at the ground state, but in some essentially non-equilibrium state. So there are sort of quick collisions.
Yes.
Should there be also the similar problem with self-interaction in electron-electron collision, for example?
Yes, if you apply functionals, density functionals to that problem, there is still a self-interaction error. There are other difficulties too. So the original density functional theory and the one that has been most fully developed is for the ground state, not for excited states, not for time-dependent states, just for the ground state, stationary state. And that's what I mostly talked about in my lecture. There's also a time-dependent density functional theory that comes from Hardy-Gross in the early 1980s. And in principle, you could also describe time-dependent phenomena by solving a time-dependent 1 electron Schrodinger equation, not an eigenvalue problem now, but a time-dependent problem. And so that should be applicable to the kind of processes you're talking about, in which the particles collide and so on, or in which there are time-dependent external fields that drive the electron away from its atom. That theory looks formally very similar to ground state density functional theory, but because there's no energy functional. Instead, in that theory, there's still an exchange correlation potential that describes the effective field that electrons see. It's a time-dependent external potential, but it should in principle be constructed separately to satisfy its own constraints, and it should not be in principle be found from the ground state energy functional, because except for very slow processes, if you have a very slow process, you can derive this exchange correlation potential correctly from the ground state functional. But for fast processes, that doesn't work. So they have a bigger problem, because they have a whole different object to approximate this exchange correlation potential as a function of time or a function of frequency. But yes, there is a self-interaction error, and if you take out the self-interaction error from a ground state theory, that will help. I think that will probably help to describe these systems better. It's just that it won't solve the whole problem for many electron systems.
Okay, thank you.
The next question from Igor Sukhenko.
Yeah. Do you hear me?
Yeah, I hear you. I hear you.
Well, first of all, just want to thank Professor Perdew for this highly inspiring talk, and it's a semi question and semi remark. I don't know.
That's okay. Comments are also invited.
I'm kind of studying the material that exactly has these kind of strong correlations. It's also like in case with cupra, it's connected to copper d orbitals, and
yes.
The pure DFT, even with Hubbard U corrections, predicted that it would be a metal. However, some people did the proper dynamical mean field theory that included two-body interactions, and they proved it. They showed it's actually a Mott insulator or something like that, and it confirmed more closely with the experimental results. So I'm wondering, because nobody has done it before, perhaps some of those scan potentials can capture this metal to insulator transition, perhaps with some symmetry breaking and something like that. Maybe I should try it.
Yeah, I would try it. That's what happens for the cuprates that I talked about. Scan plus symmetry breaking. I didn't mention it, but there is also symmetry breaking in these materials. The materials are antiferromagnetic, and that's a symmetry breaking. Scan plus symmetry breaking opened up the gap and gave many properties of the material of that cuprate material correctly. I can't guarantee that it will work, because scan doesn't have all the important exact constraints. It doesn't have this exactness for all one electron densities, but it has a chance for problems like that.
Thank you very much.
May I ask another question?
Sure.
More related to the previous one by Nicola. So regarding these hydrogen-rich compounds, which became popular due to superconductivity at high pressures. So how good DFT for modeling these compounds, and maybe perhaps R2 scan, is it improving the predictions?
I don't know the answer. I think that's a good question. So I think it would probably PBE predicted superconductivity in some of these materials. Is that correct?
I think so. There were
Yeah. Okay. I think that SCAN has a good chance to do better than PBE for these materials. I don't really know the materials, and I haven't seen this calculation done. I haven't tried it myself, so I'm not sure. But I think that SCAN has a good chance. As long as so the problem is not with hydrogen per se. The problem is with stretched bonds and odd one electron densities. If the one electron densities in these materials are not strange, if they're reasonably compact after you localize, if you can make Wannier functions that are compact, then I think SCAN has a good chance to work. A possibly related problem is the problem of liquid water and ice, where you have lots of hydrogen and hydrogen bonds. And SCAN works very well for those problems.
Mm-hmm. Thank you. So I don't see any more questions. If it's not the case, let us thank the speaker again for a wonderful talk and discussion. Thank you for your time and for your talk.
And thank you all for your good questions and comments.
So with this, yeah, please, Sergey.
Just said thanks a lot. Thanks, Professor Perdew.
Okay, let us finish the seminar then.
Okay, thank you
very much.
Bye.
Thank you. See you next time.
See you.